Pablo Jarillo-Herrero today from MIT. He is a Cecil Green Professor of Physics. Pablo got his, Bachelor of Science from Valencia, and then he moved to UC San Diego for a 2-year master, and then he decided to go back to Delft to do PhD there. He did fantastic work on nanotubes, actually revolutionized the field at that point. And then he came to Columbia for a postdoc, and he stayed at Delft for 1 year a postdoc, came to Columbia for a short postdoc, and then he started at MIT as an assistant professor in 2008, right? And then since then he has, been awarded many prizes. He worked on graphene and topological insulators mainly at the beginning of the career. Then he moved on to 2D material heterostructures, a variety of them. And then recently, there is this most exciting phenomena that is happening, that you have 2 layers of non-superconducting material, you put them on top of each other at the right angle, and then all of a sudden it superconducts. And it's not only simple superconductivity, it also looks like there are correlated states, so maybe the physics of it is actually much richer than a standard superconductivity. So it's a pleasure, and thank you for coming. Please.
Thank you very much, Dirac. So it's a great pleasure to be here. I remember when I was a postdoc at Columbia, I got invited to some event here at NYU, and met Andy for the first time there. And my good friend Barbara Uselmas, who was also a student in Andy's group. And it was in a different quarter, in a different setting. I can see that things have improved a lot, and this really looks fantastic, this building. So, and I hear that you have many visitors, and you're hiring, and lots of visitors today and the past week, including some members from MIT. So good. Things are really thriving, and it's great to see you. So I'm very happy. I always enjoy a lot to come back to New York. So thank you, Gerard, for the invitation. So I want to tell you about our experiments on magic angle graphene. Sorry, I forgot to say, here Ken Van Tilburg was a undergraduate student in my group, so it's always great to see also your, many years back undergrad, doing well. So I want to tell you about our experiments in magic angle graphene. Okay? But before I start, let me sort of put everybody on the same page and give you a little bit of context and background. So, among the most fascinating states of matter that we have are those where the interactions between individual constituents are very strong, and they give rise to what is known as strongly correlated states of matter. This is something that is very general, not just in condensed matter physics. For example, you have the quark-gluon plasma, which is a state of matter that happens a few hundreds of nanoseconds, microseconds after the Big Bang, okay, where the individual constituents are very strongly interacting, give rise to very unusual phenomena. We can recreate these states of matter nowadays by colliding heavy ions, such as people do at Brookhaven. We also have, for example, the different phases of nuclear matter in neutron stars. Okay? So this is a picture of an actual neutron star, and I got this thing from Wikipedia. These phases are actually known as nuclear pasta. So astrophysicists are very creative with names. So these phases have like lasagna face, bucatini face, spaghetti face. So I think we need to learn in condensed matter to be more creative with names. We have a PR problem there. So. And then, perhaps closer, to my heart, to condensed matter physics, you have, for example, fractional quantum Hall states of matter, where the interaction between electrons leads, for example, to behaviors which are very unusual, such as electrons seem to have a fraction of a charge, attached to them. They also can do strange things, like they obey quantum statistics, which are different from those of fermions or bosons, and many unusual behaviors that one can do when you have strongly interacting constituents of matter. Now, a large fraction of the condensed matter community is studying strongly correlated quantum materials. Okay? So now the individual constituents that interact strongly are electrons, in this case, and this again gives rise to very unusual behaviors. And there are many classes of, many families of quantum materials. You have, for example, the heavy fermions. Here, the electrons' effective mass can be hundreds or even thousands of times that of the bare electron mass. And this gives rise to very interesting behavior, non-Fermi liquid behavior, for example, in the resistivity as a function of temperature. You also have materials classes such as the quantum spin liquids, where your electron spins Even at zero temperature, they're constantly fluctuating, and they're in a very highly entangled quantum mechanical state that has very interesting topological properties. And perhaps the most studied family of strongly correlated quantum materials is that of the high temperature superconductors, where if you plot in a phase diagram of temperature versus doping or charge density, there are a number of phases here over which we have a very limited understanding, even despite decades and decades of investigation. So just to, again, put everybody on the same page, let me remind you, just from the point of view of quantum mechanics, single particle physics, what types of materials do we have in terms of their electrical properties? Yeah? So if you take single particle band theory, there are only two options, basically. Let's assume that we have we make a crystal, so we put atoms in a periodic lattice. Okay? These atoms have certain orbitals, and now you put electrons in this, in this lattice. Okay? So if you calculate the density of states as a function of energy, okay, then you have a set of bands. Okay? Here is a band, here is another band, separated by a gap. And then there are two possible options. If you put electrons in your system such that one of your bands is completely occupied with electrons, and the next band is completely empty of electrons, then you have an insulator. Okay? Why do you have an insulator? Because your electrons here, they do not have any infinitesimally close in energy empty states onto which they can be thermally excited or be excited by an electric field such that in order to conduct electricity. Yeah? So completely full band, completely empty band, this is an insulator. This is the band gap of your insulator. Then the alternative scenario is that you have this density of states as a function of energy, and you have one completely filled band, and the next band is only partially occupied with electrons. Okay? Now, at zero, you have at infinitesimally close small energies, you have available empty states. Your electrons can populate those empty states if they are thermally excited or if they're excited by an electric field, and they can conduct electricity. And therefore, you have a metallic state. And those are just the two options that we have if you only calculate things according to single particle quantum mechanics. Now, what happens if you include electrostatic interactions between electrons? Yeah? In that case, you can have a situation where one of your bands can be partly occupied with electrons, and therefore you should have metallic behavior, but due to the strong interactions among your electrons, the system actually undergoes a transition to an insulator state. Okay? This is often called a correlated insulator state. Okay? So this may happen, for example, like this. You have your Fermi energy here in the middle of a band, and now due to strong interactions between your electrons, this band splits into two bands. One of them is completely full, and the other one is completely empty. So you sort of go back to this situation. Okay? Now you have one completely full, one completely empty band, so it's an insulator, but this gap is a correlated insulator gap due to interactions between your electrons. It is not a single particle gap due to the ionic potential in your system. Okay? So there are many examples of correlated insulators. One of the most famous is the so-called Mott insulator. So what is this object? What is this material class? So imagine you have this square lattice. So we have atoms here in a square lattice. And now each of these atoms has a single orbital. In a single orbital, I can put two electrons, spin up or spin down. And now let's imagine I put just one electron per side. Okay? So I put one electron per side. This means I'm putting half as many electrons as I could put in this lattice. Okay? Because I'm putting one electron per side, I could put up to 2 electrons per side. So this, I fill it with half as many electrons as I could. Now you can see right away that in principle, in single particle physics, this should be a metal. Because since in each side I can put 2 electrons, there's nothing preventing me from electrons jumping between sides, and they can continue jumping and conduct electricity if I apply an electric field, for example. Okay? However, what happens in a number of materials is that this double occupancy of a single side can be energetically very costly if those 2 electrons interact strongly electrostatically. Okay? So we say that there's an energy cost, charging energy or an interaction energy due, such that no double occupancy of these sides are allowed. And therefore, since each of these sides has already 1 electron, and you cannot doubly occupy any of them, all of the electrons get stuck in their positions and this leads to an insulator behavior. And that thing is a mode insulator. Okay? Now, why are mode insulators? So you go back to a situation like this. Okay? This band, which you originally have with half occupied with one electron per side, now splits into one fully occupied and one fully empty. Okay? Because you've half occupied this band and a gap opens. Now, mode insulators are very famous materials because they, among other things, they are believed to be the parent compounds of high temperature cuprate superconductors. In these high temperature cuprate superconductors, you have these copper oxygen planes where in the copper atoms you have a single orbital and you can put an electron there with spin up or spin down. And in the parent compounds of these materials, you have exactly, if you don't dope these materials, you have one electron per site. And the strong interaction between these electrons leads to localization, to a mode insulator behavior, where electrons are just stuck in there. Now, an interesting game, an interesting thing happens if you remove a few of these electrons. Because now if you remove a few of these electrons, so you dope it with holes, if you remove a few electrons, now these electrons have empty sites next to them. So they can jump onto those empty sites and go from one place to the other. And they do this in a correlated fashion, which is believed to lead to high temperature superconductivity. Okay? The basics of how this happens, the essence of how this happens, is believed to be reflected or explained by this so-called Haber model, where you take into account that a mode insulator where you have emptied a few sites, you're going to have electrons that are going to be able to hop between sites, and you still take into account the fact that you have this penalty to doubly occupy an individual site. And there's again an interesting game, how does this all happen when you have a few empty sites, and such that people believe that this model captures the basic physics and essence of this phase diagram, okay? Where in this mode insulator corresponds here to zero doping, and then you have all this variety of phases, including D-wave superconductivity at high temperatures, which occurs as you dope, as you remove electrons from your system. Now, I'm telling you all the time, people believe, it seems, people think, because nobody knows how to solve this problem exactly, analytically. Okay? Despite more than 40 years and counting of this problem, nobody knows how to solve it theoretically. You have to take one or another approximation, and the starting point for these approximations are not, even the starting point from which approximation you take to solve this problem are not agreed upon among theorists. So this is a very complex problem, and because we don't know how to solve this problem, and 30 years, 40 years and counting, and we're still struggling with it, people have developed alternative approaches to investigate the physics of strongly correlated electrons and strongly correlated quantum materials. One of the most fascinating approaches that people have developed and are investigating is that of trying to recreate or simulate strongly correlated quantum materials by using ultra-cold atoms in optical lattices. Okay? So here what people do is they shine lasers against each other and they create a periodic potential where they can load atoms, and then they can tune the interaction between these atoms to mimic the physics of the Haber model or mimic the physics of strongly correlated systems. So already about 17 years ago, the group of Immanuel Bloch, Markus Greiner, they were able to load atoms in this periodic potential, and they were able to change the interaction between the atoms such that they could go from a mode insulator to a superfluid. Okay? This is something that was done with bosonic atoms, so it was a realization of the Bose-Haber model. A few years later, people did this thing with fermionic atoms, so there was a realization of the Fermi-Haber model. And the state of the art, the latest developments in this field of recreating, of simulating quantum materials with ultra-cold atom lattices, optical lattices, is the following. They have been able to realize anti-ferromagnetism in the Fermi-Haber model. Okay? So they've been able to load atoms in this lattice, and they have been able to check that they align themselves anti-ferromagnetically. Okay? So the ultra-cold atoms community is beginning to explore this corner of the phase diagram, the mode insulator and anti-ferromagnetism. They would, of course, love to explore the entire phase diagram, and in particular reach the region of D-wave superfluidity in their atomic systems. However, they have substantial difficulty in cooling down enough the temperature in order to reach this D-wave superfluidity regime. They are already working at temperatures of the order of a nanokelvin, and they have to go down about a factor of 10 or so, they believe, in order to reach down the wave superfluidity. And although there's no fundamental reason why they cannot do that, it is technically a very substantial challenge, and they are working towards it, but it will take still a while to get there. So we have these two platforms, quantum materials, such as the cuprate and many other quantum materials, where we have lattice scales of the order of an angstrom or so, very little control over these materials. We have ultra-cold atoms in optical lattices. Here, the typical separation between these atoms, so typical lattice scale is of order of 1 micrometer, and you have perfect control with your lasers, to do everything that you want in the system. And what I want to tell you about today is about this magic angle graphene, where the natural superlattice scale is of order 10 nanometers, so it's about a factor of 100 from either of these. And the natural energy scales associated with phenomena here is also intermediate between these two extremes. For quantum materials, you typically have energy scales of the order of 100 or 1,000 Kelvin, depending what you're looking at. For ultra-cold atoms, typical energy scale temperature is in nanokelvin. As you will see, the typical energy scale here is of the order of 1 Kelvin. Okay? So intermediate between these two extremes. So this is the outline of my talk. I'm going to tell you a little bit about 2D materials, Legoland, twistronics, plenty of new modern terms people are adding to the field. I'll then tell you about graphene and magic angle graphene superlattices, what are those? Then I'll tell you about our observation of correlated insulated behavior in the systems and superconductivity. And then I'll end with an outlook and some of the latest news and what's going on since we announced our discovery. So I'm sure you've been exposed to a variety of talks on graphene and 2D materials. For 15 years now, we've been able to, there are three-dimensional materials which are layered, and we've been able to isolate an individual unit cell, so 1 atom thick or few atoms thick of these materials, and investigate their properties. They turn out to be different from the properties of the 2D material, happen to be different from the 3D bulk counterpart. This is fascinating. Graphene was the first to be isolated. By now, we have hundreds of these materials. Now, very soon after people start to investigate the properties of individual layers, they realize, well, we have one layer from this material here, we have another layer from this material here. We just put one on top of each other and look at their properties. Turns out the properties of the combined system are different from the properties of either of the constituents. So this led many people to make these analogies, and my friends and colleagues wrote even these reviews making an analogy of these two-dimensional, they're called van der Waals materials, and then van der Waals heterostructure, these analogies with Legoland and Lego pieces, where you stack the pieces on top of each other. Now, I don't know how many of you have played recently with, or ever with Lego. I have small kids, so I play with my kids with Lego, and often they're very small, so they come and say, like, Daddy, I can't get the piece to stick on top of the other. And as you know, in order to build a Lego structure, your pieces have to be aligned perfectly, 0-degree angle, one piece with respect to the next. Okay? You don't have much freedom there. Okay? So in my opinion, although this van der Waals Legoland aspect of 2D materials is very important, and it leads to many very interesting properties, we have analogs of that. For example, semiconductor heterostructures or metallic superlattices. We have Lego after all. I think the most unique aspect of 2D materials, which does not have any precedent in the history of material science, is the fact that we can do this. We can put two-dimensional crystals on top of each other with an arbitrary angle of rotation between the two crystals. Okay? But there's something that you could not do before. There's some crystals that happen to grow with some dislocation at some angle or something like that. But what I'm telling you is that I can put one 2D material on top of another 2D material and choose the angle completely at will. It can be 1 degree, 57, 33, 24. I can do anything that I want. Okay? And this twist angle degree of freedom can lead to dramatic changes in the electronic, optical, and mechanical properties. And as I will show you later today.
Energetically the same states, or
sorry?
Energetically are they the same state, degeneracy, or they are
no? So that's a very interesting subject itself of research. What are the energetics of these two-dimensional crystals when you rotate them one on top of each other? For some materials, there seem to be minima in the potential energy, so they prefer some angles. But I'm telling you that we're able to fabricate these devices with any angle that we want, okay? And it stays at that angle. Yeah,
Okay.
we can do that. Okay? So let me stop this before you get too busy. So let me talk a little bit about graphene and magical graphene. So graphene is a honeycomb of carbon atoms. Okay?
So sorry, just to finish. So
Yep.
those are local minima in some sense. I mean, it's a
Yeah.
long-lived structure that you are
Yeah.
creating, and we have local
It
minima.
is known that there are some shallow local minima as a function of rotation angle between structures, but we're able, because of disorder, because of other forces which are competing with that energetics, we're able to actually fabricate devices at any angle that we want. Yeah? And they are stable. So this is graphene. It's a honeycomb of carbon atoms. All of these atoms are carbon, so they're chemically equivalent. Okay? However, from a crystallographic point of view, there are two types of atoms. It turns out, in order to tile a honeycomb, you need 2 unit vectors and 2 types of atoms. And we call them the A and B sublattices. Okay? But they are all carbon atoms, but crystallographically, they are distinct 2 sublattices, the A and the B sublattice. So you can calculate in a simple quantum mechanical model what is the electronic structure, the energy versus momentum for the electrons in graphene. Turns out to be like this. This is your reciprocal space, your Brillouin zone, and if you zoom in near the corners of your Brillouin zone, you have this very peculiar energy momentum relation, which is linear. Yeah? This is, usually you have parabolas, for your kinetic energy. In electrons in graphene, you have this linear energy momentum dispersion that has led to all these analogies with ultra-relativistic massless particles for electrons in graphene, etc. Okay, this is the same dispersion that you have for photons, for example, except that, of course, electrons in graphene are fermions. In fact, this energy momentum relation dispersion is captured by this equation, which is nothing else but the Dirac equation in 2 dimensions for massless particles. Okay? You see here, energy is linear in momentum. This spinor in the Dirac equation usually is spin up and spin down of the electron. In the case of graphene, this is a pseudo spin, which tells you whether the weight of your electron weight function is on the A sublattice or on the B sublattice. Yeah? Now, another thing that you have to take into account is that there are these, several of these double Dirac cones in the graphene electronic structure. Only 2 of them are independent. The other one are sort of copies by reciprocal space lattice vectors, but we have 2 of them, the K and the K prime values. And then we have also spin. So this means that the electrons in graphene have this 4-fold degeneracy. They can be spin down, up, spin down, valet K prime. Just remember 4 for the rest of the talk. It will appear later. Okay? Now, what happens if you put graphene on top of graphene and you rotate? Okay? So you form a moiré pattern. Okay? So you form a super periodic structure when you put 2 periodic structures on top of each other at an angle. The wavelength of this moiré pattern is the distance between the soccer balls that you see here. And that wavelength, that moiré wavelength, depends on the angle of rotation between the 2 sheets. In the case of graphene on graphene, because these are 2 identical lattices, the moiré wavelength can go all the way to infinity when you align them exactly to 0. Okay? So this is what happens in real space. Let's see now what happens in reciprocal space, and therefore how is the electronic structure modified for this system. So we have here graphene. This is the reciprocal space. This is the Brillouin zone. This is a Dirac cone. Okay? This is the entire graphene electronic structure. Let me put another graphene sheet on top. Okay? And now let me rotate. Okay? If I rotate the 2 graphene sheets, okay, the reciprocal spaces also rotate by the same angle. And this means that the Dirac cones, these are the Fermi surfaces associated with, my Fermi energy is up here, because it's 2-dimensional, I have a Fermi surface which is a disk. Those disks get separated in momentum space. Okay? So twisting these 2 layers of graphene leads to the Dirac cones that represent the energy momentum relation of electrons in one layer and the other. They get separated in momentum space by a distance in momentum, which is proportional to the sine of the angle. Okay? So now, let me start from a small angle so that the separation in momentum space is proportional to the angle. Sine of the angle is equal to the angle. Okay? And then let's go towards smaller and smaller and smaller angle, and let's see what happens. Okay? So I'm going to start from this. I have here my two Dirac cones. One represents electrons in one layer, the other represents electrons in the other layer. Their separation between the two Dirac points, is proportional to the angle. Now, this would be a situation that would arise if the electrons in one layer didn't see the other layer. But this, when I put two graphene sheets on top of each other, they're just 3 angstroms apart. So the electrons are very much aware that the other layer exists, and they can tunnel between the two layers. Okay? This means that at this point in the electronic structure, where you have sort of this intersection of the Dirac cones, at those degeneracy points, there is level repulsion, okay? Similar to bonding, anti-bonding states in a molecule, so that a gap opens there. This gap opens there due to interlayer interaction. Okay? Now, this is the situation that occurs when this interlayer interaction is smaller than the energy at which that crossing point occurs. If I now reduce the angle, these two Dirac cones get closer and closer and closer. So you have to think about this. I have my Dirac cones, and then as I make the angle smaller, these Dirac cones are getting closer and closer and closer. At this intersection point, there is this level repulsion, which flattens, brings one band down. So as I get closer and closer and closer, eventually this thing flattens to the bottom, to 0 energy. Yeah? So if I keep decreasing the twist angle, I reach a value of an angle for which the interlayer interaction is similar to where that crossing point is, so you form a flat band. You push that bottom band down to 0. This condition is called a flat band condition, and it happens at an angle which was coined by Bistritzer and McDonald as the magic angle. Okay? This magic angle value depends on the interaction between the two graphene sheets, and it happens to be 1.1 degrees for graphene on top of graphene. Okay? Now, I should say that there was an earlier paper by Suarez and Morel where they calculated this flat band condition. They got the angle wrong. McDonald and Bistritzer got the angle right. And then there were also some experiments, some scanning tunnel microscopy experiments by the group of Eva and Dre at Rutgers University. It turns out that there's a feature in the spectroscopy. If you do a spectroscopy of graphene, there's a feature associated with this gap, with this Van Hoff singularity that occurs here. And they saw that Van Hoff singularity, the energy went to 0 at about this angle. So there was already some hints that something funny was happening at this angle electronically.
Is there some phase transition at that angle? Is there auto parameter which characterizes this?
No, for now, all you have to think of is that there is this flat band that happens at 0. And now, what does that lead to? I'm going to be telling you about. Okay? But for now, this is a single particle calculation. They interact, flat band.
And as you keep going smaller,
I'm going to show you. Okay? Now, this is a schematic cartoon of what happens. Let me show you, actually, in a calculation, what is it that happens. Okay? So remember, we have the two graphene sheets with the two reciprocal spaces. If I join the corners of these reciprocal spaces for the two graphene sheets and I complete this hexagon, this is my superlattice Brillouin zone, because I have a real space long moiré wavelengths. In reciprocal space, my superlattice Brillouin zone is smaller. Okay? Long in real space means short in momentum space. So this superlattice Brillouin zone is smaller. Here I'm going to show you a calculation of the electronic structure of this twisted bilayer graphene as a function of rotation angle. I start with 3 degrees, which is a large angle. Okay? As you can see, for this large angle, the electronic structure looks identical to graphene. This just looks like 6 Dirac cones, okay? Similar to what I showed you before. So the first thing that I'm going to do, I'm going to rotate the angle towards smaller angle. The first thing that you're going to see is when I go to smaller angle, the wavelength, the moiré wavelength becomes larger, which means the superlattice Brillouin zone is going to become smaller. It's going to rotate and become smaller in momentum space. And so that's the first thing that you're going to observe. And then you will see how the electronic structure gets modified. So I'm going to run a video. There, so you see the electronic structure is evolving with angle. A set of bands appears, which are isolated via band gaps from the next set of bands. And at 1.1 degree, this is becoming very flat there. And then it continues to evolve in a complex manner. Okay? Now, because my students spend a lot of time working on it, let me run it again. So you can admire it. So this is a set of bands, isolated bands that appear. It's going to become flat at about 1.1. And then it continues evolving, okay? And that's something else. So let me, turns out that if you include the lattice relaxation, It's actually a very interesting problem of how these lattices relax to adjust to each other for small angles. If you include lattice relaxation, this magic angle happens to be closer to about 1.05 degrees. Although this value keeps evolving as calculations get better and better. Yeah? So let me take a cat down that flat band there. Yeah? So this is the energy versus momentum for that. You can see this no longer looks like this linear Dirac dispersion of graphene. It looks like it's not 100% flat. There is a little bit of dispersion, but it's orders of magnitude flatter than the graphene dispersion. It says that the Fermi velocity is orders of magnitude smaller than it was in graphene. Huh? Now, this is energy momentum, and this, this blue set of bands is these flat bands. Now, flat in momentum space, if you now do the Fourier transform to go back to real space, this means highly localized in real space. Okay? The Fourier transform of flat thing is a delta function. So, if you calculate what is the charge density in these flat bands, happens to be highly localized in certain regions of this twisted graphene structure. Okay? In particular, you have very high density in regions which are locally have this, what we call AA stacking. Locally, all of the carbon atoms are on top of all of the other carbon atoms, locally. Of course, in reality, we have a small angle, so there's a shift towards a different stacking pattern, which is called AB stacking pattern. Only some atoms are on top of the other atoms. The B atoms are on top of the A atoms, but the other ones are not on top of each other. So these regions of high charge density are separated, tunnel coupled, the little tunnel coupling is what leads to the small dispersion, by regions of AB and BA stacking pattern. So from the top, you can look at it, and it looks like this, schematically. You have this moiré pattern, okay? This is a moiré unit cell, and you have these AA stacking regions where the charge density likes to be, and these are separated by AB and BA stacking regions. Okay? So if I do a little bit more, schematic, with the lattice, this is what it looks like. These AA stacking regions are separated by 13.4 nanometers at this magic angle. Okay? And this is what's going to be my, in quotes, triangular Fermi-Hubbard lattice, on which I'm going to put now electrons and look at the interactions. Okay? Now, I say triangular in quotes because the AA sites from a triangular lattice, triangular means hexagons with a dot in the middle, but as you can see, the ABBA regions form a honeycomb plaquette. So it's actually a honeycomb lattice in reality. This actually took some time for the theorists to find out. So let me show you, some data. Now, before I show you the data, let me show you how we fabricate these devices. Okay, this is something that people always ask me.
Can I ask you a question?
Yep.
So what would be, if I were to come up with some simple function for a dispersion relation in the flat band, what it would be? Like energy equals to, let's say, quadratic with some tiny number? Or
it's highly complex, because the thing that I showed is a little bit of a simplification. In reality, the electronic structure is very complex. And this is actually subject of current research, exactly how it looks. Okay? It depends on what's your angle on 0.005 degrees increments, and it varies very fast. Okay? So let me show you how we fabricate our devices. So, the thing that we do first is we take a glass slide with a polymer, sticky polymer on it. Okay? And then we bring a substrate which has a hexagonal boron nitride flake on it. Boron nitride is this layered material. It's also a two-dimensional material. We don't take a single layer. We take something which is something like 20, 30 layers. It's a very convenient, ultra-flat, ultra-clean dielectric substrate for graphene devices. Okay? So then we come with this sticky polymer, and we pick up this hexagonal boron nitride. That's the first thing. Thousands of groups around the world can do this thing. Then we bring a substrate which has graphene on it, an isolated one, atom-thick sheet of graphene. That thousands of groups around the world can also do this. But the thing that we do, and this is a little bit special, is we position our hexagonal boron nitride sort of halfway on top of the graphene sheet. Now I bring my boron nitride down, and I tear the graphene piece in two. Okay? So from the top, now this looks like this. I have my substrate with half of my graphene sheet. I have my glass slide with the hexagonal boron nitride, and the other half of the graphene piece on top of it. Because these two pieces of graphene come from the same flake, they are crystallographically aligned with respect to each other, even though now they are at different heights. So now I can rotate let's say my substrate, by any angle that I want, in particular 1.1 degrees, why not? And then I can shift it on top, and I stack it. And then I pick up the bottom graphene, and I have these two graphene sheets aligned with respect to each other at 1.1 degrees, okay? Pretty uniformly over a large area. And then I can continue to do nanofabrication of my devices, okay? Yeah?
When you tear it, doesn't it bend?
No. There's some strain on the edges maybe, but the center of the pieces are still aligned with respect to each other amazingly. Yeah.
How do you detect the position of the graphene and the or nitride?
Oh, you just look through an optical microscope. These are visible.
You can
You can
see
see
the
single
graphene?
atom thick sheet objects. Yeah, no problem. So, okay, so we end up then fabricating, we pick up another graphene and a hexagonal nitride flake such that we end up with this twisted bilayer graphene, which has a bottom and top hexagonal nitride, so we have a nice clean sandwich there. We can contact them with source and drain electrons so that we can apply a voltage, measure a current, and very importantly, we have a nearby metallic plate, metallic electrode, that forms a parallel plate capacitor with the graphene system. So that when we apply a voltage, a gate voltage to the system, we can vary the charge density of one of the plates, on the plates of the capacitor. Okay? But one of the plates is the graphene, so we change the charge density on the graphene with the voltage knob. Yeah? That's very important. So now let me remind you, how does graphene conduct? Okay? You measure the conductivity of regular graphene as a function of density. If your Fermi energy is deep in the valence band, you have lots of holes, so you have a lot of conductivity. If your Fermi energy is deep in the conduction band, you have lots of electrons, so you conduct very well. If your Fermi energy is at the Dirac point, you don't have much charge carrier, so you conduct poorly. So graphene versus density have this V-shaped conductivity. Yeah? And this has been seen by thousands of groups. Right? Now, let me show you what happens when you have graphene on top of graphene. Let me start with graphene on top of graphene at a very large angle of rotation. Okay? At a very large angle of rotation, graphene on top of graphene just looks like graphene. So the conductivity versus density looks like V-shape. And I'm normalizing here. I'll show real units in a moment later. For now, I'm just normalizing the density here to what I call NS, the superlattice density, which is how many electrons can I put in this moiré unit cell, which is actually 4. You know, spin up, spin down, valley K prime. Remember, I told you 4 will appear again. So I can put 4 electrons or 4 holes in this moiré unit cell, and I go from one band edge to the next band edge. So, this just looks like V-shape because, graphene on graphene with a large angle looks like graphene. Let me now show you data from a device with a smaller angle, but not yet magic, but smaller angle. Okay? 1.8 degrees. Now within the energy window accessible to our density that we're shooting here, we have near charge neutrality. This still looks like those graphene Dirac cones. So you have V-shape near charge neutrality. But now, as I add 4 electrons to my system, I hit this band gap, so the system becomes insulator before I can start adding charge to this upper band and start conducting again. So I go through this insulator behavior when I put 4 electrons per unit cell before I conduct again. If I remove 4 electrons or I add 4 holes, I do the same thing. I reach this insulator behavior before I conduct again. So this insulator behavior is due to these single particle gaps. Okay? In reality, interaction effects renormalize these gaps, but to zeroth order, we can understand this based on a single particle behavior. Remember, when I'm half occupying this band, this system is a metal, it conducts very well. Let me show you now what happens if we take a device with a magic angle. Right? So I take a device with 1.08 degrees. Near charge neutrality, I still have sort of graphene Dirac cones, so I have this V-shaped conductivity. At full filling or full emptying of the superlattice, I have also 0 resistance. But now, halfway through, when I put half as many electrons as I could in this band, or half as many holes as I could in this band, I get an insulating state. Okay? The system should be a metal, but it's not a metal, it's an insulator. Okay? So let me show you now, these are real axes, in units in millisiemens for the conductance, and in density of electrons in units of 10 to the 12 per square centimeter. This is a 2D material. Just to remind you, from charge neutrality in this direction, we're adding electrons. to our system. From charge neutrality towards the left, we're adding holes in the system. Okay? So when we saw this insulating behavior that have filling, we realized it was very unusual. And there were several pieces of information that led us to conclude that it's even more unusual than we thought originally. One is, this behavior only happens when you make devices where the rotation angle between the two sheets is 1.1 degrees plus minus 0.1 degrees. Okay? So you only see this behavior, okay, this insulating behavior, for angles very close to 1.1. If you're 0.2 degrees away from 1.1, you do not see any of this. So it's clearly tied to this flat band condition. Okay, I will comment on that more later. The other thing that was very unusual is that if we now apply a magnetic field to this system, okay, and it doesn't matter if we apply it parallel to the graphene sheet or perpendicular to the graphene sheet, but it's more striking that it happens when we apply a perpendicular field, this insulator behavior turns into a metallic behavior. Okay? So if we measure the conductance near this region or near this region, black means insulator, red means metallic. As I apply a magnetic field, I go from insulator to metallic. Now that's extremely strange. A magnetic field makes electrons rotate. So it typically localizes electrons. It doesn't make them conduct better. Yeah? So, I've measured thousands of graphene devices many times, and other 2D materials. Typically, when you apply a perpendicular magnetic field, you either go from metal to insulator or from insulator to a stronger insulator. You never go from insulator to metal. That's very, very strange. Yeah? So basically, after a number of other experiments and so on, and to cut the story short because I want to show you the superconductivity data, what we came up with was the following. There is this set of flat bands, okay, in graphene. This is charge neutrality point. When we tune our Fermi energy such that we have half as many electrons as we can put in this conduction band, or half as many holes as we can put in this conduction band, interactions between the electrons lead to a correlated gap that turns your system into an insulator. This correlated gap is probably formed, made out of singlet states. When you apply a Zeeman magnetic field within a Zeeman field, okay, you polarize those bands so that you close the gap, and now they have band overlap, you can start conducting. Okay? So this picture is probably an oversimplification. In fact, a lot of the theory work that has happened in the past year is aimed at exactly understanding how this thing happens. Okay? And we called in our paper, we said that this is a mode-like insulator state in the sense that it's something that occurs when you put half as many carriers as you could put in these bands. But exactly what type of correlated insulator state is still subject of debate. Now, this is something that happens not only for graphene on graphene. There are a number of other systems by now that have been investigated that exhibit similar physics. So, there are a number of moiré superlattices that you can fabricate, and in particular, the group of Feng Wang put something called ABC trilayer graphene on hexagonal boronitride. It also forms a superlattice, a moiré superlattice, and they reported similar mode insulator-like states, okay, at half filling of their bands, and they posted the paper shortly after ours. Now let me show you about our, the superconductivity. So, so we had this data, conductivity versus density. But these data are in devices which are measured in a two-terminal geometry. What does it mean? It means we have a source and a drain contact, just two contacts. This is a geometry which is very convenient if you want to measure an insulator. Because if something is going to have infinite resistance, you do not care that you're adding a little bit of extra resistance with your contacts. However, if you want to see if something conducts very well, okay, you do care if there's some parasitic series resistance, so you want to change type of device geometry. So when we were measuring these devices in two-terminal, remember, from here to the right, we're adding electrons. We call this the correlated insulator state for electrons. From here to the left, we're adding holes. We call this the correlated insulator state for holes. So when we look at the temperature dependence of these devices, here around the correlated electrons, not much happens, The system is an insulator. When I cool down, it conducts less. That's what insulators do. Okay, that's what we expected. But then when we looked around the correlated holes, for the insulator state itself, it was the same thing. Colder, conducts less. But right next to it, this thing seems to conduct more the more we cool it down. Okay? So we saw that conductance enhancement, and we're like, that's kind of strange. Let's see how well does this thing really want to conduct. Okay? So I told my students, let's make 4-terminal geometry devices. So basically, you do the exact same fabrication, except that now you have several electrodes, and you can run a current between these two electrodes and measure the voltage drop within your device, and you eliminate all parasitic resistances. So let me show you data from another device. This is a 1.16 degree device. This is the conductance. We first characterize these devices in 2-terminal geometry because it's simpler. So this is a 2-terminal conductance as a function of density. We've got this V-shaped near charge neutrality, insulated state at 4 electrons or at 4 holes per superlattice unit cell. We have stuff going on at 2 and -2. We also have stuff at 3 and -3. There's a lot of extra things which I'm not telling you about that happens also in this system when you have other integer fillings of your superlattice. This is in the presence of a small perpendicular magnetic field. If I now remove the magnetic field, not much happens around the correlated electrons, but a lot happens around the correlated holes. Okay? So now we switch to our 4-terminal geometry measurement, and what happens is the magic angle twisted bilayer graphene superconducts. Okay? These are data from 2 devices, 1.16 and 1.05 degrees. The resistance versus temperature experiences a dramatic drop of several orders of magnitude below our noise floor. Okay? This thing has 0 resistance at low temperature. You can measure the VI curves, so you can run a substantial current through your device without any voltage drop in your device. You can do any test that you want of 2-dimensional superconductivity. This is a 2-dimensional superconductor. Okay? And now remember, we have this gate voltage, this knob, with which you can vary the density of carriers in our system. So the thing that we can do, and that has attracted, perhaps the most attention is the following. So we can zoom in this region, and now we can measure the resistance as a function of temperature and density. We have this region around 2 electrons, 2 holes per unit cell, where we have a correlated insulated behavior. We add a few extra holes, and we have a superconducting dome. We add a few extra electrons, and we have a superconducting dome, a smaller superconducting dome. So when my students show me this, it immediately reminded me of the hundreds of times that I have seen pictures like this. Okay? This is the phase diagram of the high temperature cuprate superconductors. Now for some reason they get the axis for hole doping, electron doping wrong. Let me flip them for you. Okay, now it's correct. So at half filling, they have a mod insulator state. With 0 doping means 1 electron per site, actually. Okay? The doping is relative to that state. So 0 means 1 electron per site, half as many electrons as you can put. If you add a few extra electrons, you get a small superconducting dome. If you add a few extra holes, you get a large superconducting dome. Okay? Here we have a correlated insulator state when we put half as many electrons as we can in these bands. If you add a few electrons, you get a small superconducting dome. If you add a few holes, you get a larger, wider superconducting dome. Okay? The difference is that in order to plot this phase diagram, each point in the x-axis here is a different chemical growth, a different crystal, and typically of a different material class, because not all materials can be grown in all doping ranges and for electrons and for holes. So you have to grow thousands of materials, literally, to do this. Here, I go from here to here in 10 seconds with my voltage knob, in a single material with a single disorder realization. Okay? And that gives us a lot of tunability and flexibility. So now this situation that I'm depicting here, where these 2 domes are similar in size, usually we have actually a situation which is much more asymmetric, where we have a much smaller superconducting dome for electrons than for holes. And in these cases, we also have substantially higher critical temperature for these angles. Okay? Our highest critical temperature when we reported this data was 1.7 Kelvin. I'm going to show you more data in a moment. So this is a 2-dimensional superconductor, so you can apply a magnetic field to kill superconductivity. You can measure the resistance of different magnetic fields to extract superconducting coherence lengths. You can apply perpendicular and in-plane magnetic fields. Because it's a 2-dimensional superconductor, you can apply much larger in-plane magnetic fields, okay? Because there are no substantial orbital effects, because it's 2D. So in fact, you can do all of this again continuously because you have your density knob. Okay? So these are the resistance versus density and versus now perpendicular magnetic field. So you have the superconducting domes, okay, but now in magnetic field rather than in temperature. But when my students showed me this data, I was like, You know, it's not as pretty as the previous data, you know. These temperature numbers, you know. What is all this crap, you know? What is all this noise? And then we realize, it's not noise, actually. This thing is periodic. It looks periodic. What happens? You have a two-dimensional superconductor that you're switching between superconductor and insulator. So if you tune your chemical potential in between, what does this say what to do? Do I become superconductor or do I become insulator? Well, it does both. Okay? It segregates into islands which are superconducting and insulator. So if you pair your chemical potential at these boundary regions, and now you measure the critical current as a function of perpendicular magnetic field, you have these Fraunhofer-like patterns which tell you that there is Josephson interference through your superconductor where there are a set of superconducting islands connected by insulating islands, and typically a couple of these islands dominate, so that it gives you mostly a pattern which we can recreate typically with a single squid with either symmetric or asymmetric Josephson junctions. Okay? But this is very interesting because it tells you that there is phase coherence, Josephson effect through your system, which confirms, if there was any doubt, that this is a two-dimensional superconductor.
If you look at the period, will it really come out to be like a cell or moiré cell? Or?
So we can look at the period. It turns out it's not the moiré unit cell, and it's not the total device. So it probably means it's segregating, and it, you know, some island, you know, that it chooses, you know, that is the final island, you know, when you're there at that, you know, intermediate density. But yeah, we can do experiments to control this so that we make on purpose a given squid. Now, I just told you that the maximum, you know, critical temperature that we have is of the order of a Kelvin, you know, 1.7 Kelvin. Now I'll show you data with a higher, you know, critical temperature. So we might wonder, okay, so how strong a superconductor is this twisted bilayer graphene, right? After all, these cuprates have TCs of 140, 160 Kelvin. So what's the big deal? Now, you don't usually compare superconductors based on their absolute value of the critical temperature. That's of course very important, okay, for applications if nothing else, okay? But the way you typically compare superconductors is you say, okay, how high is the critical temperature for this superconductor given how many electrons does it have that can contribute to the superconductivity, right? And this is something that is typically plotted in something which is called the Uemura plot. It's a log-log plot of critical temperature versus density properly normalized by degeneracies and effective mass, or you can think of it as Fermi temperature. Okay? So in this plot, in this corner of the diagram, most of the conventional superconductors lie in that corner of this diagram. Okay? So for example, have aluminum. Aluminum has a critical temperature of 1 Kelvin, but it has an enormous amount of electrons. It has a Fermi temperature of over 100,000 Kelvin. Okay? So given how many electrons I have in aluminum, it superconducts pretty modestly, okay, at a TC of only 1 Kelvin. As you go from this corner in this direction, you typically go towards more exotic and unconventional types of superconductors. In this blue band here is where most of the unconventional superconductors exist. Okay? So you have, for example, high temperature cuprate superconductors here, you have the iron pnictides here, you have the organics, you have the heavy fermions. I put even data here for ultra cold atoms, lithium-6, potassium-40, both axes multiplied by 100 million so that they appear here. But in terms of coupling, they're the strongest coupled systems, you know, that we have, these ultra cold atoms, because the strength of the coupling is tunable here. So where is magic angle graphene in this plot? Happens to be right there. It's one of the strongest coupled superconductors that we have. Okay? In fact, in 2 dimensions, is the lowest density superconductor by well over an order of magnitude with respect to the next lowest density superconductor. In fact, if you measure the superconducting coherence length, okay, the size of our Cooper pairs in magic angle graphene is just a little bit bigger than the interparticle, than the moiré unit cell. Sorry, than the interparticle spacing, okay, in terms of density of electrons. Super low density. Our Cooper pairs are just barely bigger than the interparticle density.
It's like bound here then, real bound.
So we are, I mean, this means that we are pretty close to the BEC-BCS crossover. Okay, compared, you know, relatively close. We're not there yet, but compared to other systems, we're among the closest to that position in an isolistic system. The only other system which has a little bit bigger coupling is iron selenide monoray STO, which is also an ultra strong coupling superconductor. It has very high TC for the density of electrons that they have. Now, so, you know, there are many, many questions that remain. You know, the one that I get asked the most is what is the origin of this correlated insulator behavior and the superconducting or the parameter. And in case you haven't been paying attention to the archive, this is just a small list. I stopped updating this 2 months after our paper. Now there are another 200 papers, here. We're trying to explain, what's going on in our system. I come from graphene and 2D materials physics, where I always tell people that the angular cone of disagreement between theorists is about 20 degrees, more or less. So if you look at this list of papers, the angular cone of disagreement is 2 pi. In fact, it's actually 4 pi. It's no directions. So to me, this is something a little bit new. To find that there's so much disagreement. People have predicted all kinds of orders, all kinds of S, P, D, S plus P plus D plus F, all letters of the alphabet, or the parameters. So the first paper was by Senke Xu and Leon Valens that predicted D plus ID chiral topological superconductivity. That's one of the preferred options. So they published the paper 2 weeks after we posted the experiment. Very interesting. I guess 2 years to do the experiment. Takes theories 2 weeks to just explain everything. So that's also. Now, but I want to talk about that paper, and I'm not going to talk about any of these things. I only want to mention this paper, Bolovic. Posted a paper just shortly after Leon Valens. And he said, he also sent us an email, Pablo, finally someone has done experimentally everything that I predicted. So we get lots of emails from theorists like that. So that's not the surprising thing. The surprising thing is that he said, he posted a 1.5-page paper where he said, look, for years, for decades, people have been reporting ultra-high temperature superconductivity in graphite, including room temperature. This is going back to the 60s or even the 50s. Okay? A few reports each decade, unconfirmed, the data a little bit strange, but consistently, a couple of papers per decade, room temperature or above 100 Kelvin superconductivity in graphite. And then Bolovic, 4 or 5 years ago, so well before our experiments, he said, you know what? This is too many reports to be ignored. Let me tell you what happens here. All of these experiments have been done in turbostratic graphite. Graphite where the graphene planes have small angular misorientations between the layers. When you have that, you can calculate that this thing will result in flat bands in your electronic structure of graphite. And you put your chemical potential in those flat bands, you're going to have correlated superconductivity with very high critical temperature. So as I was reading this thing, I was like, oh wow, oh wow, oh wow. Like each page was like, whoa. So basically he said, finally, someone has done the controlled reproducible experiment, all controlled. Now just add a few more layers and get room temperature. Just start right there. So he encouraged us to try. We'll see. I used to think that those experiments on graphite were totally crazy. Now I'm like, I don't know. Who knows? Could be. Maybe there's something there. So let me, in the last, minus 2 minutes, just tell you a little bit about the outlook and what has happened since. So we reported our discovery last March at the APS March meeting. So what has happened since then? One thing that has happened is that we have reproduced ourselves many times. That's always good. It doesn't always happen, so it's good, when you can reproduce yourself. So we have a lot more devices. These are a few of them. That was last summer. Now we have plenty more. We have TCs now of the order of 3 Kelvin and above. Even better than you reproducing yourself is that someone else reproduces yourself. No? So by now, 5 other groups have independently reproduced our results, which is very, very encouraging. The one that was published just a few weeks ago in Science was by the group of Corey Dean in collaboration with Andrea Young. Not only they reproduced our results, they also extended them in a very interesting way. I told you before that this magic angle condition depends on what's the interlayer coupling between the 2 graphene sheets. So my Harvard theory colleagues and myself, we predicted the following. If you have an angle which is not the magic angle, it's a bit larger, if you can somehow increase this interlayer coupling, you may make that angle be the magic angle, because it will have the right angle for a given interlayer coupling for it to develop flat bands. So we calculated what is the pressure that you need to apply in order to convert a given angle into a magic angle. So, for example, 1.47, 1.12 degrees is magic, so has flat bands at ambient pressure. 1.47 is not magic, the bands disperse. You apply pressure of a certain amount, it becomes flat. 2 degrees, not magic, apply a bit of pressure, apply more pressure, it becomes flat. So we calculated the pressure dependence of the magic angle condition. Yeah? And what this experiment in Colombia, what they did is they had this device. The first thing that they did is they made a device at the magic angle, and they saw correlated insulators and superconductivity. They reproduced our results. Then they made a device with an angle slightly larger, 1.27 degrees, as you can see there. It's not 1.1 plus minus 0.1. No correlated insulators, no superconductivity. Then they applied the exact pressure that we calculated, and correlated insulator happened, and superconductivity. Then they applied more pressure, and the behavior went away. So they demonstrated that indeed this flat band condition, can be tuned, and it's necessary in order to observe this correlated behavior and superconductivity. It was a beautiful experiment, just published a few weeks ago. So more things that have happened is that as we investigate more and more the system, we realize that there are more and more analogies and similarities to other strongly correlated materials. For example, we observe these various types of superconductor insulator transition and metal insulator transition physics, which is all tunable with gate. In particular, we also see linear resistivity behavior, which seems to indicate strange metal type of Planckian dissipation type of physics. So in this phase diagram of the cuprates, you see that above this D-wave superconducting dome, one of the strangest phases is this thing called strange metal, and they call it strange because they have no idea what it is, okay? So it's strange, And strange means the behavior of many properties that you can measure about the system is strange, okay? It doesn't follow what you would expect from a regular Fermi-liquid metal. And one of the things that it is characterized is by a linear resistance versus temperature. So in our system, if we take the resistivity up here, we have superconductivity at low temperature, and then we have this linear resistivity with temperature. Okay? This is a case where, because this is relatively high TC, this behavior is interrupted, but we can take another sample where TC is much smaller, and then we have this linear resistivity behavior down to almost zero temperature. Okay? And in fact, this temperature, which is 25, 30 Kelvin here, may not seem like very large compared to the cuprates, but remember, this is an ultra low density system. The Fermi temperature is actually about 30 Kelvin, so this is a temperature range which is equivalent to reaching several thousand Kelvin for the cuprates. So, we've done that. We have also measured anisotropies in the critical magnetic field of the superconducting state. Okay? So this means that the system, superconducting state of our system, is spontaneously breaking rotational symmetry. It chooses a direction for the order particle. Okay? This is something which is called nematicity. So you have the system is a superconductor, and if you measure the resistivity versus angle of your in-plane magnetic field, you have these two lobes. Two lobes means an ellipse in polar coordinates. Okay? So let me show you the ellipse. It looks like this. And of course, all of these things, we can measure them as a function of density, as a function of temperature. We have so many tuning knobs here compared to other systems. It's very rich. As you can see, this ellipse changes direction of the axis, which tells you this is not a simply a nematicity due to strain. It's something else which is going on. It's of electronic origin. And this is something that happens in many correlated materials, and it has deep implications for the type of superconductivity. Now, let me just last thing is tell you that so far I've been telling you about action happens around the correlated holes. By now, we also see action happening, superconductivity, etc., around the correlated electrons. In fact, we can look at correlated electrons, correlated holes around holes and electrons, and all kinds of maps, and we see superconductivity everywhere. Okay, so now it's much richer, the phase diagram that I showed you before. And perhaps the last thing I want to end with this is that this is something much more general than just graphene and graphene. Okay? We have now 2D materials that exhibit all the condensed matter behaviors that exist around. Yeah? We have 2D materials that exhibit behavior, topological, Dirac, semi-metal, and others. Insulators, we have regular semiconductors, we have superconductors, which are themselves two-dimensional, like iron selenide, titanium selenide, high-density cuprates themselves can be isolated in monolayer form. We have also magnets and quantum spin liquids. And all of these materials, you can take one, put it on top of itself, and in some cases, different materials on top of each other. And by choosing either a magic angle, or in many cases, just a small twist angle, you will, if the material didn't have correlations, strong correlations like graphene, you will introduce strong correlations. If the material had already existing, was correlated, you will modify those correlations. Okay? So now there's a booming field, and by now several different materials classes have been found when you low twist angle them, that they exhibit superconductivity and correlated insulated behavior. There's a large material classes theories that are crazy, calculating magic angles for all materials, correlations for various twist angles. It turns out that not only this is bringing together the 2D materials community with the strongly correlated materials community, these flat bands that form in the systems very often are topological. They have finite Chern number. So also the topological physics community is coming together in this system. So it's very rich, and there are many, many, many possibilities. So with this, I want to end with perhaps the most important slide. This work is largely the work of my graduate student Joan Sa, together with Bala Fatemi for the earlier work, and then Daniel Rodin and Oriol Rubius for the more recent work, and also in collaboration with many people, including the Vanjan Chowdhury, who I hear was here yesterday, giving a talk. So he's really a fantastic theory postdoc. He has been helping us a lot with some of our work. And then together with also Harvard people, Japanese collaborators. And here's my group enjoying dinner at home. And thank you for your attention.
If I understood correctly, when you have a multi-insulator, it is equivalent to having a field valence band. That's why you have
Half field.
Yeah, it is field, so you have an insulator. Then you remove one electron. I do not understand why this results in a superconductor rather than a conductor, because you don't have any Cooper pairs.
We don't remove a individual electron. We tune with density, and we remove a number of electrons in units of 10 to the 12, right? What we remove is a fraction of an electron per unit cell, okay? Per moiré unit cell. This results in a superconductor. Why and how? Nobody knows. Same way nobody knows about how the cuprates become superconductors when you remove electrons from a multi-insulator, okay? So it still remains to be explained. Nobody has a model yet for how that has happened.
Very beautiful work. Have you tried tunneling into this system? I mean,
So it's one of the experiments that we want to do. Okay, we have tunneled in the past. Last year we published a paper 2 years ago about tunneling into a graphene Josephson junction proximatized by external superconductors. We want to repeat the same experiment here because tunneling can give you information about the type of order parameter. But
I'm also thinking above, if you see some of the pseudogap physics.
yes, so that's very interesting. A lot of people have mentioned, people have already paid close attention to some of the physics that, we have behavior here before the system becomes, let me show you data with a finite magnetic field. Okay? So we have, this thing was becoming superconductor, now it's a metal because finite magnetic field. It can become an insulator, but in between metal and insulator, there's also these curves which intersect the axis at a finite value of resistance at 0 temperature, which is behavior very similar to the pseudogap behavior in some cuprates that exhibit certain type of charge order. So when people saw this, they immediately told me, Pablo, I think you have a pseudogap there. So we want to do these tunneling experiments to see both what type of gap we get, either the soft or a hard gap, and to see if we have pseudogap behavior. We have several other indications of pseudogap physics in addition to this, and it is expected because it is ultra low density Cooper pair in 2D. So they expect this fluctuations to lead into pseudogap
Is
physics.
boron nitride the problem for immediate measurements or not?
No, we know how to use boron nitride as a tunnel barrier to the tunnel. It's mostly, this is all very recent and there's a lot of experiments to do, but it's high on our priority list of experiments to do.
Any other suggestions?
It was really fascinating, and congratulations.
Thank you.
I didn't get why, if I understood what you're saying about the conjecture that making it thicker, making more layers, you would get a higher temperature. And have you, what's the impediment?
So we haven't tried, okay? We will slowly try, but as you can see, to get 2 layers to superconduct, we needed to know theoretically within 0.1 degrees precision what we have to aim at. Nobody knows for multi-layers, which angles should we choose? Should we choose theta magic, theta minus theta, theta 1, theta 2, which what values, This is still, people are calculating slowly. Now, in principle, because we are already at the strength of coupling, which is almost the highest you can be, okay? So we can gain a tiny bit more in length of coupling, you know. But we already have samples with TC close to 3 Kelvin, similar density. We're not going to reach room temperature or anything like that by gaining strength in coupling. Okay, we're already pretty high. The only way to move to high temperature is to go diagonal in this plot, which means increasing the density of electrons. And in fact, if the cuprates had the same strength of coupling that we had, they would be room temperature superconductors, more or less. So how do we increase this density of electrons? One idea is like, oh, just increase your, decrease your moiré wavelengths, decrease the size, and that will give you, higher TC, which is what part of the motivation to increase this pressure, to do pressure studies at larger angles. I think that realistically will take us maybe to 10, 20 Kelvin, something like that. You cannot reduce that much more the density. Basically, you can see here, you need atomic scale lattices, densities, angstroms, in order to reach room temperature, given a maximum coupling. So I don't know exactly the mechanism how in graphite they achieve. I don't think there is a real prediction. I think it was more a conjecture that this is what happened. Okay, I don't think there was a prediction with, and you will get this thing and exactly it will happen. Yeah? So I don't know very well if there's an answer to how exactly the mechanism for reaching a particular TC value. I think it's more about how Volovic thought about why this happened, and we highly coupled, strongly coupled superconductivity was correlated. I don't recall him predicting a value for TC.
And maybe I didn't grasp it properly, but it seemed like the behavior with respect to magnetic fields was really totally different, and the issue of magnetic fields being destructive to the superconductivity might work really differently, so that you could use it for.
No,
that'll still be an issue.
No, I mean, magnetic field destroys superconductivity, okay? It's just that this is a very anisotropic material because it's two-dimensional, so out-of-plane magnetic fields kill superconductivity much faster than in-plane. And then in-plane, you have anisotropies because of this pneumaticity. So, it's unusual, but still, the basic fact that magnetic field kills superconductivity is there. Yeah.
Since the superconductivity is happening in this really small kind of twisted layer structure, is there any idea if you take one of the magnetic materials and you stick it right there, does that automatically kind of kill superconductivity, or do you have some kind of weird coupling now there too? Because it's a little different than like a normal material if you just sort of magnify it.
Excellent question. We have nowadays two-dimensional materials which are magnetic. Okay? So, in fact, we showed in my group, 2 years ago, the first two-dimensional crystals which are magnetic. We can, in principle, stack it on top and see how it affects superconductivity. Who kills, does the superconductor kill the magnet because it's also one layer only? Or does the magnet kill the superconductivity? It's a very interesting experiment that we have to do, but we haven't done them yet. Sure. Another thing that, I thought your question was perhaps in the following sense, in the cuprates, the mode insulator state is antiferromagnetic. Yeah? A lot of people are investigating, theories are investigating, and experiments we are trying to also look at what is, if any, the magnetic order of our correlated insulator state. There are many predictions to what it could be: ferromagnet, antiferromagnet, cantilever ferromagnet, photospin liquid, singlets of all kinds. So this is something that remains to be investigated. And unfortunately, you cannot do neutron spectroscopy. You don't have material. This is ultra tiny, flakes. So you cannot do the usual things, apply the usual tools that you apply to study magnetism. You cannot measure magnetization because, again, you have sensitivity. But there's some probes that we have with scanning nanosquid and epicenter magnetometry and other things, and people are slowly starting to apply to them.
I can ask one more question, I guess. So in thin film like aluminum DCS, right, when you apply in plane field, then it's very thin. You actually get like a very well-defined saturation. We call it quartz, and then there's a paramagnetic limit basically. Right? So in yours, I guess you have a curve. Does that match like a D-wave kind of prediction of what you're supposed to see at very thin?
So I think you refer to this Pauli limit for the critical field of the, yes. So in the paper that we published, we saw that we violated the Pauli limit by a little bit, not too much. So given the fact that the transitions are broad and so on, we didn't dare say we violated the Pauli limit, and therefore this is exotic, okay? It could be, given the transitions are broad, that when you choose a better definition of critical field, we're still within the Pauli limit. And we didn't realize back then that it was anisotropic in plane. Now we have better measurements in plane. And it seems like we violated a little bit more than before. So we're starting to be borderline between, you know, I wouldn't say that, you know, if you want to say like, oh, we really violate Pauli limit, you want to be maybe a factor of 2 or 3. We're not quite that level, but we're doing more and more investigation. This is something that a lot of people have told us, that if you clearly violate Pauli limit, this would have deep implications for the type of, you know, order parameter that you could have. So.
Okay, sounds good. Very interesting. Any other question? If not, let's thank Pablo again.